Okay. Hello everybody. Today's topic is fuel cells, stacks and systems. A short repetition: a fuel cell works in a way that an electrolyte is separating the fuel and the air side. On the anode side you have an oxidation reaction, on the cathode side a reduction. The electrons travel through an outer circuit, are used as electricity, and ions travel through the electrolyte. One fuel cell. Now I here illustrated the example of a solid oxide fuel cell. But one fuel cell delivers a voltage of circa 1 volt. And this is not determined by the type of fuel cell, but it is determined by the gases present on anode and cathode side. So typically if you have hydrogen and air, then the voltage of the cell would be around 1 volt, and you can calculate this actually by using the Nernst equation. So it doesn't make a difference if your cell has the size of a button or if it's 1 meter by 1 meter large. In addition, this 1 volt is only valid at open circuit voltage. In other words, when you don't operate the fuel cell. As soon as you operate the fuel cell, you will decrease the voltage. So in this figure you see the current voltage characteristics in the green line. So if you increase the current, that means you draw a power out of the fuel cell, which is shown in the yellow curve. Then your voltage is decreasing. So you can not achieve the 1 volt under operating conditions or when you use the fuel cell. So it will be slightly less than 1 volt. In order to achieve higher voltages, you can stack a number of cells on top of each other. And this is illustrated here in the next slide. So in fact you separate each cell by a so-called interconnect or bipolar plate, and then the next cell is added to this stack. In that way the cells are connected in series, so you add the voltage of one cell towards the other. Is shown here. And we had already which properties the components of the fuel cell need to fulfill, and here there are few properties of the interconnect material listed. We expect that it is electron conducting because you collect the electrons from the interconnect plates. It should be tight, gas tight or electrolyte tight, so that there is not crossover, and it should also be gas tight for air and fuel, so they should not meet and mix each other. And of course it should also be compatible with the fuel cell main components, the electrodes. So in that way we create a stack, and we can increase the voltage by the number of cells we have. So in this case I sketched 5 cells, would give circa 5 times 1 volt. And if you operate the stack, of course the voltage would be slightly lower. So depending on the desired voltage output, you have to stack the cells. I have here illustrated a few pictures from the internet for some 3 types of fuel cells, and you see it's really a stacking of fuel cells, so single cells divided or separated by the interconnect plate, bipolar plate. In these examples you have a solid oxide fuel cell, PEM fuel cell, and an alkaline fuel cell. You can find it for others, and the geometries are specific to the specific developer supplier, if it's a square geometry, a round geometry, or even a third type. Now you have a stack with the desired number of cells and the desired capacity to deliver power. In order to integrate this into a system or a product, you have to add more components, and they are usually called balance of plant components or BOP components. First thing, of course, you need to add fuel and air. So you need gas connections for fuel and air inlet outlet. In addition to that, both fuel and air might require some pre-treatment in order to be able to be accommodated or to work in the fuel cell. So this treatment depends very much on the type of fuel cell you are working with. And I just call it pre- and post-processing of the gases. This could include cleaning. For example, PEM fuel cells work with very pure hydrogen, so a cleaning step might be needed. It could be a humidification step. And also maybe a catalytic pre-conversion. If you use natural gas or biogas as a fuel, you might require a catalytic conversion to arrive at hydrogen or carbon monoxide to enter the fuel cell. And also after the fuel cell, there might be needed an additional post-treatment of the exit gas, for example an afterburner, because you will not have a complete reaction of the fuel. So you will have a small concentration of fuel exiting the fuel cell, which usually has to be removed from the exit gas. The next component you would need is to treat the electronics. You need connections for electricity to extract from the fuel cell, and typically you would like to have alternating current. The stack provides DC, so you need a converter. And the third main part here is the heat management. The fuel cell reaction is an exothermal reaction, so you have to manage the heat that is formed. Usually the stack is cooled, in example of a solid oxide fuel cell, by blowing air through the stack, which takes away the heat that is formed by the exothermal fuel cell reaction. There are many more possibilities to integrate the heat and also actively utilize the heat. So you have a finally higher total efficiency of the fuel cell when you combine both the electricity output and the heat output. So there are different options listed here. For example, a preheating of the inlet gases by the exit fuel heat by heat exchangers, for example. So these are the main components of the system, and they vary a lot depending on the type of fuel cell you are using, the degree of purity of the fuel used, the state of the fuel, gaseous or liquid, and so forth. This is an example how it could look in reality, and this is an example from Osaka Gas, so you are welcome to visit the homepage, and it shows clearly the components, the balance of plant components in different colors. You have number one, the fuel processing. In that case, this unit is a combined heat and power unit. It provides electricity and heat to households. It has a smaller scale or size in the range of 700 watt. That's why it is called micro combined heat and power, micro CHP. And it is typically connected to natural gas or city gas. It can contain either a PEM fuel cell or a solid oxide fuel cell. And depending on the type of fuel cell, you need to have the pre-treatment of the natural gas or city gas. You need to have a reforming step. You have a CO separation step if you use the PEM fuel cell, and so on. So you can look onto the homepage to see the details. And also it's a very nice picture to see that left part of the picture, the very small one, is actually the fuel cell unit. And all the others, the big part shown here, is the heat storage in a water tank. So the fuel cell unit, all the balance of plant components, they are in this small compartment. I selected the next example from the mobile sector. In this case, it is a fuel cell hybrid car with a battery, so a battery fuel cell vehicle used for mobile applications. And in this specific case, it uses bioethanol as a fuel. It was inaugurated in Brazil, where there's a lot of bioethanol available. And in this particular case, a solid oxide fuel cell is the type of fuel cell used, and this is connected to a battery, can be fueled by the bioethanol, which is processed in the green and orange part in this system flow sheet. These were two examples on how you can integrate the fuel cell into a system together with balance of plant components. And there are of course many more in different applications in the small scale, large scale sectors, in mobile stationary applications where the details might differ to a great extent. This concludes this part, fuel cells to systems. Thank you for your attention.